In part 1 of our lesson on law of cosines, we will derive the law of cosines. To accomplish this, let's consider triangle ABC with one vertex at the origin. So you can see point C is here and its coordinates are 0, 0. Since this is angle A over here, we know then its opposite side would be lowercase a. Angle B is here, so its opposite side is lowercase b. And with angle C being here, its opposite side is lowercase c. Next, we will determine the coordinates of point A and B. B is pretty easy to find. We know since it's on the x-axis, its y-coordinate has to be 0. And since the length of this side of the triangle is A, we know then the x value here would have to be A. Now over here, we can find the coordinates of point A if we use our trig definitions. So let's come over here for a minute. We know that when we use our trig definitions that we have theta in standard position and we have a radius going out to the point on the terminal side of theta. Now, comparing that to our picture of our triangle, this angle right here we know is angle C. So in this picture, theta is equal to angle C on our triangle over here. We can also see that from the origin out to the point, which is R in our trig definitions, in our triangle, that is side B. So R is equal to B. So if we use our trig definitions, that x over r is equal to cosine theta, and we solve that for x, we get x is equal to r cosine theta, and now we are going to make these substitutions. Where there is an r, we will substitute b, because that is the side of the triangle, and where there's a theta, we will substitute that with angle C of our triangle. Then x equals r cosine theta becomes x is equal to b cosine of C. So that means the x coordinate of the point here at A is going to be b cosine of C. Now, using our trig definitions, we know that y over r is equal to sine theta, which means y is equal to r sine theta, and we can make that same substitution so that y is going to equal b sine of C. So we come back over to our triangle, and the y-coordinate here is b sine of C. Next, we're going to use the distance formula to find the length of side C in the picture. So we know that C will be the square root of the x-coordinate at A, which is b cosine C, minus the x-coordinate at B, which is A, and we have to square that, plus we do the y-coordinate at A, which is b sine of C, and we subtract the y-coordinate at point B, which is 0, and we square that quantity. So now let's simplify this equation. Notice in the second step, I have c squared, so that will remove that radical. And now let's go ahead and take this binomial and square it. We know from our algebra days that we have to take the first term and square it. So that would be b squared cosine squared c. We have to subtract double the product. So that would be 2 times a b cosine c. Then we have to add the second term squared. So there's an a squared plus, here we're subtracting 0, so all we have to do is square the b sine of c, so we get b squared sine squared of c. Now I'd like to reorder these terms. First, I'm going to write the a squared. Next, we have plus, I'm going to write this first term, b squared cosine squared of c. Then I'd like to write this last term next, so plus b squared sine squared of c. And then finally, we will subtract the 2ab cosine of c. Now we have a squared plus, from these two terms, we can factor out a b squared, and we would have left cosine squared of c plus sine squared of c. And then we bring down the minus 2ab cosine of c. Now, using our Pythagorean identity, we recognize that cosine squared of c plus sine squared of c is equal to 1. So this equation becomes a squared plus b squared minus 2ab cosine of c. And this is the law of cosines. Let's explore this equation a little. Notice that here we have isolated a side, and then over here we have that side's opposite angle. And then the other two sides appear here, a squared plus b squared, and here in this product, 2ab. So given a triangle, ABC, we can actually write 3 forms of the law of cosines. So let's start out writing the one we just got. C squared is equal to a squared plus b squared minus 2ab cosine of c. Now we could also write it isolating, for example, the b side. So if we said b squared, that's going to equal the sum of the squares of the other two sides, so a squared plus c squared minus 2 times ac times the cosine of b. Because remember, whatever side you have here, its opposite angle is the one that's in the cosine argument. And then finally, if we isolate a squared, then we know we have to put the other two sides as b squared plus c squared minus 2bc cosine of a. Because if I have side A isolated over here, then I have to have angle A in the argument of the cosine. When you're solving triangles, there are only certain situations when you can use the law of cosines, and the two situations are when you have side angle side or when you have side side side. Now what side angle side means is if two sides and their included angle are known. So if you have two sides of a triangle and you also have the included angle for those two sides, then you can use law of cosines to solve that triangle. The other time you can use law of cosines is when you have side, 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 and what that means is all three sides are known. One big difference between the law of cosines and the law of sines is that the law of cosines does not have an ambiguous case like the law of sines does. So let's explore why that is. To help you understand this, let's review the positive and negative signs of the trig functions by quadrant. We know that cosine theta is going to be positive in quadrant 1 and quadrant 4 and negative in quadrants 2 and 3. Now let's also consider where the inverse cosine lives. We know that the inverse cosine only lives in quadrant 1 and 2, so if we're taking the cosine inverse of a positive number, then it will output an angle between 0 and 90 degrees. Whereas if we take the cosine inverse of a negative, it will output an angle between 90 and 180. So when we solve an equation like the law of cosines and we get down to the last step where we will be solving for cosine theta equals something, when we use our cosine inverse, we know that we're either going to get a quadrant 1 or quadrant 2 angle. Now, if we get a quadrant 1 angle, then we know that angle will be between 0 and 90, which would be an acute angle of the triangle. If we're taking the cosine inverse of a negative number, then cosine inverse will output an angle between 90 and 180 degrees, and that is an obtuse angle. And both of those angles would be possible in a triangle. It's possible that a triangle could have an acute angle between 0 and 90. It's possible that a triangle could have an obtuse angle between 90 and 180. Now let's compare that to the sine function. We know that sine of theta is positive in quadrant 1 and it's positive in quadrant 2. And it's negative in quadrants 3 and 4. And if we come over here to the inverse trig functions, we know if we're taking the sine inverse of a positive, that will output a quadrant 1 angle, so in degrees, that would be between 0 and 90, and certainly a triangle could have an angle between 0 and 90. But sine inverse, the only other quadrant it lives in is in quadrant 4. So if we're taking the sine inverse of a negative, then our calculator is going to output an angle between negative 90 and 0. And there's no triangle in the world that can have a negative angle in it. So there's a big difference between using sine and cosine. Notice also when the sine is positive, then the angle could either be a quadrant 1 angle between 0 and 90, or the angle could be a quadrant 2 angle between 90 and 180, and that's the ambiguous case. We don't know whether that positive value for sine is leading us to an acute angle or an obtuse angle. But because cosine theta is positive in quadrant 1 and negative in quadrant 2, it is not ambiguous. If we have a positive cosine, it's an acute angle. If we have a negative cosine, it's an obtuse angle. Another way I think you can look at this to help you understand is we know that in the law of cosines, there are only two special cases when we're even allowed to use the law of cosines. And we know that's when we have side, side, side given, or side, angle, side given. Now let's explore these two cases a little bit. Suppose you were given 3 sides to make a triangle with. So we have the first side, and the second side has to be that long, and the third side has to be that long. If you are given these 3 sides, then there's only one possible triangle that you could make with those 3 sides. When we combine these 3 sides into a triangle, there's only one way that we can have them hook up with each other to actually make a triangle. So in the case when we're given side, 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 there is only one possible triangle. Now let's look at what happens when we're given side, angle, side. So here, maybe we have this side is given, and this side is given, and this angle is included. So that's our side, angle, side. Well, if those are given, then there's only one possibility for that third side. It's going to have to be right there. Only one possible triangle again. Now let's compare that to what happens when we have to use the law of sines. When we're using the law of sines, we could be given 2 sides and a non-included angle. Remember over here for side, angle, side, this was 2 sides and the included angle. So 2 sides and a non-included angle, we can say side, side, angle. So let's just make a note of that. 2 sides and the non-included angle. So let's see what that would look like. So maybe we have a side here, and that's our first side, and maybe we have this angle but not this side. So I'll just put a dotted line so that we can mark the angle. So we're given this one side and this one angle, and then we can't have this side because then it would be side angle side. So we have to be given a side over here. Now what happens is when we have side, side, angle, this is the ambiguous case because this side wouldn't have to go here. This side could swing over here and end up connecting over here. And so in this case, this is where we are getting the two possible triangles. And that's the ambiguous case. And the reason this happens is because sine of theta is positive both for acute angles, which would be this bigger triangle, and for obtuse angles, which would be this smaller triangle. Whereas with cosine, we know that cosine is positive if it's acute and negative if it's obtuse. So that's why law of cosines does not have an ambiguous case. Let's take a minute now and review some geometry. Remember that a triangle can have at most one right or obtuse angle. So that means the other two angles are acute. In other words, then, every triangle has at least two acute angles. Secondly, within one triangle, the larger angle is opposite the longer side. So when we're comparing sides in a triangle, we can know which opposite angle will be the biggest. Third, it makes sense then, if a triangle does have an obtuse angle, it must be opposite the longest of the three sides. Then it follows that the angles opposite the two shorter sides are guaranteed to be acute. So let's look at a couple triangles and make sure that you're understanding this. In this first triangle, we see that 13 is the longest side, and pretty easy to see that angle Y, which is opposite the 13, is the obtuse angle in the picture. And angle X and angle Z are both acute. So the obtuse angle was opposite the longest side of the triangle, and the two sides of the triangle that were shorter, both of their opposite angles are acute. Let's look at this triangle now. We know that 8 is the longest side, but we can see that the angle that's opposite of 8 is not obtuse. We can see that it is an acute angle. So just because it is the longest side doesn't mean that its opposite angle will be obtuse. It just means its opposite angle will be the biggest. Then the angles that are opposite the two shorter sides also must be acute. So this triangle happened to have 3 acute angles, where this one had 2, and that's what this sentence is saying, where it says every triangle has at least 2 acute angles. We know that opposite the smallest side and the medium side, those two angles are guaranteed to be acute. Same over here. Opposite the small side and the medium side, those angles are absolutely 100% guaranteed to be acute. Now, the biggest angle may be obtuse or it may be acute. We don't know just by knowing it's opposite the biggest side. When we use the law of cosines to solve for an angle, we will know immediately, with no ambiguity, whether or not that angle is acute or obtuse. So a good triangle solving strategy is to first use the law of cosines whenever possible to solve for the largest angle first. Then you'll find out right away whether that angle is obtuse or acute. Second, after that, you may then use the law of sines without being concerned about the ambiguous case, because you would know that the remaining two smaller angles must be acute. And we like to use the law of sines wherever we can because it's a little bit shorter and quicker than using the law of cosines. The great thing about using the law of cosines is that it has no ambiguous case, so you will always know if you have an obtuse or an acute angle. And just a reminder, you can only use the law of cosines in two cases. So this whenever possible part here, remember we can only use law of cosines when we have side, 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 or side, angle, side. So if you have either of these two situations, you can use the law of cosines first.